Okay. So this talk that I will present now is a little bit unusual because I won't talk at all about dynamics. So let's get that straight. I will concentrate on remapping, which, as we saw, is quite an important building block of many numerical techniques, as we saw. And okay, it's I must mention that it's in the framework of the ICOMEX project, and it's a joint work with Yann Lordesoif and Thomas Dubos. So I will briefly present the problem and the general strategy for conservative remapping. Then I will talk about computation of whites. The pointer. Okay. So there will be quite a geometrical part of the talk that will concentrate on computation of intersection of spherical polygons. And then I will talk about optimization to get a logarithmic complexity. And then I will present a test case. There is just one test case because it's quite a fresh project. And I can tell you that this result is also quite fresh. And then I present my conclusions. So conservative remapping has, we often take it for granted, the remapping step, but it has quite some potential uses. For example, the most basic one maybe is post-processing. So you produce a result on one mesh and you want to visualize it on another mesh. Then you have everything that is related to coupling. So you solve an equation on one mesh, and you solve a second equation on another mesh, and you've got to switch from one description to the other. And for example, in particular, adaptive mesh refinement, or everything which entails regridding. And remember that it's important that if you have a remapping step in the algorithm, the order of the dynamics is bounded by the order of the remapping. You can't never get if you have a higher order scheme, but you have bad remapping. Okay, it's quite useful. So the requirements of a good remapping scheme, what would they be? It would be conservative, conserve mass. It would be a high order, of course, because of this, of course. Positivity, which I won't talk about now. And of course, computational efficiency is very important. Okay. So what is exactly the problem? So we're giving two meshes. So a source mesh, S, and a target mesh, T, on the sphere. And we get the functions values at the centers of the source mesh. So it's a discrete description of the function. So we've got basically an n vector, and that's where the problem comes from, that you've got finite memory on the computer, and you can't really get at the function directly. And you've got to switch to another finite dimensional description of the same function with some, you've got to suppose that your function is reasonably well behaved, for example, smooth, okay? And you've got to find the values at the centers of the target mesh. Such that, so what is the conservation requirement exactly? It's that okay, the integral, the total mass of f on the source mesh is equal to the total mass on the target mesh. But of course, how to define this if you have only this discrete description? So there is a quadrature scheme here. So these are, of course, the areas of the cell. So you can consider this as, of course, quadrature weights in this discretization. So we can introduce the F bar, which stands for the elementary mass of the function on one element. Okay, this is quite clear. So you have so this was a global conservation. You can also have notions of a local conservation. For example, if you have an area, a subset of the mesh that is called U, that is both a union of elements of the source mesh and a union of elements of the target mesh. And you want that on a U such like this, you have the same requirements, that the mass is the same on this local patch. Okay. So we will, there is an inherently conservative technique to do conservative remapping. It is that if there exists an underlying decomposition L of both meshes, so it can be constructed as the mesh of all intersections of the first and the second mesh, here the red mesh and the blue mesh. So you take all the intersections and you get the mesh of intersections, or usually called super mesh. This new mesh, you can decompose the elementary masses of the source mesh on the super mesh. If you have this, then you have won, because you can define the elementary mass on the target mesh to be the decomposition of the subgrid of the sub-elements that compose the mesh elements, and you've got that the relation, the conservation relation holds. So basically you want to have this. So to have this, we will search for necessary conditions to get this. So how can you have, what do you need to define this? You have to compute the weights, so the areas of all intersections. And you also have to find suitable FL values, so the values of the function on the super mesh. So you've got basically to do a reconstruction of the function on the source mesh that has possibly some subgrid reconstruction. So you can have the first order scheme. So you get basically a direct projection of each element on the elements of the super mesh. Or you can have a more accurate description of your initial functions. Here, for example, by piecewise affine reconstruction, and then you project on the space of piecewise constant functions on the super mesh. But you gain an order of accuracy. So, of course, here to compute, how do you compute the gradients? Of course, you do this by basically in 1D. It's easy. You can do some finite difference here. Possibly weighted by the area of the cell, and in 2D it's also very simple, because you have this nice Gauss formula which expresses the gradient in with the values of the neighboring elements, the values of the function on the neighboring elements, and you've got a direct discrete level, a discretization of this, that here on the cell Sk, you can express the gradient here in function with the sum on all elements neighboring K. So on this, you compute this circulation on the yes, you compute this sum on Vk, and these are basically the centers of the neighboring element. Okay. Of course, you've got to compute the areas. You've got to know the areas of all neighboring elements. You've got to know these neighboring elements. So you've got possibly to reconstruct the connectivity of the mesh if you don't know it. So what happens? You have that in the first order reconstruction, you get that the reconstruction of the super mesh is very straightforward. Is just the value of the function on the parent source cell. Whereas in second order, you correct this value with the help of the gradient that you've just computed. These are, of course, the centers of the center of the cell of the super mesh and the center of the source element. And now let's check that in both cases, so with first and with second order, you've got in both cases the fundamental relation that guarantees conservation. So if you've well computed of course, the areas, so you get in the case of first order, this is easy because you get FL, which is FK. So it just remains the sum of the areas of the decomposition of the source element, and you get exactly what you want. And in the second order case, you've got this term that is a new term here, which is the term of affine correction. So you've got basically to show that this holds, you've got to show that this sum here vanishes. So it's a necessary condition for your remapping to be conservative, that this is 0. So we search basically for necessary conditions. So what does this imply? It implies that GKCK should be 0 because you've got a gradient on the sphere and it should be tangent to the sphere. So this should be true. But if it's not true at the numerical level, at the discrete level, because possibly your gradient isn't computed with, is computed, for example, with first order accuracy, and you don't have exactly this. So for your scheme to be exactly conservative, you can do an orthogonalization of the gradient. It means you compute the gradient with the Gauss formula that we saw, and then to ensure this orthogonality, you orthogonalize it with this. So if you have this, and you further have this, what is this? It is the part of the sum that remains. If this is 0, so what happens? It is true if we have the barycenter, the centroid of the source cell, that is the barycenter of the elements of the supermesh. So this you've got possibly to recompute the barycenter to be sure that this holds. So in any case, you can enforce these two conditions. And then you've got that your scheme is conservative. Okay. Now, the problem that remains is how to compute exactly this weight AL to ensure that the sum is equal to the sum of the initial element. So the problem basically is to find exactly, to compute the intersections of two polygons, or two spherical polygons, but it's not very, it's not really more complex to be on the sphere than to be on the plane. I will show you. If you can compute this intersection, then the area, it's easy to find because you can find it by this beautiful formula of spherical geometry that expresses the area of a polygon if you have the sum of its angles. So this holds on the sphere. It's also called Girard's theorem. So what is the procedure? You loop over the sides of both polygons. So you have here, there are two polygons. You've got to imagine that, it's spherical polygons. So you just see this in 2D, but the algorithm is really the same. So you loop over the sides of both polygons. You take the first side of the first polygon, AB. So what do you find? That A is exterior to the second triangle. B is also exterior to the second triangle. So how do you define, a good question would be, how do you define exterior on the sphere where it is the part of, the triangle cuts the sphere in two, and the interior is where the centroid lies, of course. So you get that A and B are both exterior to the second triangle, and also that AB does not intersect the triangle at any place. So basically, you can dump AB. It's not part of the intersection. Then you continue. You take BC, And you see that B and C are both exterior too. But there are two intersections here and here that you can call B prime and C prime. So you just keep that bit. And you continue the loop. You go to CA, both exterior, no intersections, you dump it. So you basically only you have this. Then you will loop on the second triangle. So side D, you get D interior, E exterior. You've got one intersection, so you keep just the part that goes from the intersection to the interior point. EF, you dump it. And then you see that DF, what will happen? You will have one interior point, one intersection, so you will keep just this. And it's finished. You've got the intersection. So you've got to make sure that common sides, if you have counted in some degenerate cases some sides twice, you've got to make sure that you just counted once, and arrange the sides in natural order, of course, to have a closed polygon. And that's it, basically. Now, so the problem is quite solved in two polygons. We can compute weights easily. But, okay, the real problem is that we don't have two polygons, but two sets of big N polygons. So, if we search for all intersections with a no intelligent method, you will have an n squared problem, of course, if you check for all k and m if the element of source and target intersect. So it's not good. It's, of course, very expensive. You've got to make sure that intersection computations are local. So you need, basically, for a fast search algorithm for potential intersectors. And we can note that the same algorithm can be used to find the intersections with another mesh, but also the neighbors on the same mesh for the computation of gradients. Because basically, what is a neighbor? It is an element that shares exactly one side with our element. So what you do is a hierarchical division of space. You arrange the elements of the source mesh. You wrap them into their circumcircles here in blue. And you call these nodes. Why nodes? Because you will construct a tree, a search tree, and the nodes are enclosed in turn into higher order nodes here in purple, so that each big node contains a bounded number of other nodes. So this looks like an unusual tree, but it is not exactly, because you can have, of course, intersections here. That's the price to pay to have a geometry that is compatible with the spherical distance. So in tree view, you have this. So what will be the algorithm? Finally, it is a recursive search. At level 0, you test if your target element intersects the root node. And at level n, if you have your element that intersects node P, you search for intersections between this element and its children. And you must do this for all the children, of course. And of course, you can see that too many intersections of nodes slow down the search. So you've got to to build the tree smartly, in fact. So this can be done in pre-processing. So I will not get into details in the construction of the tree. It is just built bottom up. It begins with an empty root of level 1, and then you insert source elements into the tree. The center of the big node moves to the barycenter of its children, so that its radius is minimized, and the radius is updated to enclose the children, so that the root grows when you insert elements. And when the number of children reaches a threshold value, the node is split in two, and a new root is created. And when you insert it into a higher order node, it means that you search for the closest child and you insert in the child. So this works like this. Now, close with a bit of a test case. Spherical harmonic of order 2, that is it's a sectorial harmonic, this one. So we found the conservation error close to machine precision. It's 10 to the minus 12. And here is basically the interpolation error. This is the conservation error, and this is the interpolation error with the analytical f in a norm L infinity. And you can see here that the order 2 looks quite okay. It's quite a bit noisy to do a log-log plot, but it has a nice profile. And computation time is, as it should be, quasi-linear. So you have here, you may wonder about the units. It is milliseconds. And here is kilo elements. So you've got basically 8 seconds for 100,000 elements. That's okay. Can be optimized for that. So the conclusions, we built a conservative remapper almost up to machine precision with second order interpolation, logarithmic and logarithmic complexity. We even see quasi-linear. And the ongoing work is the parallelization. So there are quite some problems to solve here, but it seems favorable. And the big part is the conservation of vector quantities, and we've got to settle about what does it mean. I mean, what do you want to conserve? Because there are many linear forms that exist on vectors, and what is the priority? Thank you.
Questions? David.
I have 2 questions, both of which could be summarized as why have you made different choices from Patrick Farrell? So I guess if you're working this area, you're familiar with what Patrick did, and there's 2 things you've done differently. The first one is that he chose to make the Galerkin projection between the 2 spaces that you're working with, which is in some sense optimal, at least in L2. I'm wondering why you're not doing that. And the second thing is that when you do this search algorithm, you seem to be chucking out a really important piece of information. Because I agree, if you've got 2 random sets of polygons to intersect, then what you have is a really clever idea where you search down a tree. But you don't have 2 random sets of polygons, you have a mesh, and because you have a mesh, you have adjacency information. So once you have one intersection, you can walk through the mesh, not in order n log n time, but in order log n time, because it's an order 1 operation to find your neighbors and compute the local supermesh operation. So why are you doing extra work?
First, about the optimization techniques. This is actually a way to avoid Galerkin optimization. So you don't have, of course, there are patch recovery methods and things like that. But here, you have a method that is inherently conservative. And you can, if you compute the intersection areas and everything in pre-processing, basically, all the work is done. And so when the weights are computed, everything is stored, and you have basically an n also complexity, because you get all local information that you need.
I suppose in the finite element speak, this is like how to recover second order if you're doing P0 Galerkin projections.
Yeah. The search algorithm?
Yeah, so what was your question?
So you have adjacency information, so you don't need n log n.
Yeah, because you don't, if you have the connectivity, everything is easy, of course, but we suppose that the connectivity is unknown. Just.
But it's mesh.
It's known.
Yes, you suppose that you have you've got just some polygons that are given, and you don't even know what the neighbors are. Because we place ourselves in the setting of complete generality. So in general, you may not have information about who are the neighbors.
When will you ever not have that information? It's a mesh.
Okay. If you read from certain file formats, then you don't have the connectivity information. So that's why we want to be able to reconstruct that. In the case we don't have it. If we have it, we'll use it.
Did I see Rob raising a hand? No? Okay. Any other questions?
Actually, I did have a question.
Okay.
If you're offering me a question.
Yeah.
The last plot, why is the quadratic not steeper than the linear?
Yeah.
Which one?
Why is the blue line flatter than the red line?
Why it is flatter? Because basically it's the L infinity error. So it should be. This is yes. I didn't say what is this. It is the characteristic length of the element.
Well, you're saying order 1 and order 2, so I mean the classic question for me is like, why is the one not faster than the other?
Because it's not a one.
Yeah, it is. It is.
So the thing could be.
It means
being a spherical harmonic.
it means that the error is quadratic in h, if h is the characteristic length. So basically, it means that if you go from here, the order 2 decreases faster. If you had, for example, a scheme of order 1/2, you would have something that looks like a square.
I mean, it's just that you're okay.
One more, just here.
When we implemented our remapping, we computed the intersections in the long nut space, and this required a polar transformation. How do you do that?
We don't need. There are two things. Here we are interested about unstructured meshes, and we don't need a polar reconstruction. But of course, one limitation here is that the formulas that I showed, for example, the defect formula for angles to compute the areas, it is limited to sides which are great circles. So basically, if you want to do this works for remapping from an unstructured to an unstructured grid. If you have to deal with the lat-long grids, there it's not direct. You should be able to generalize the area formula, or you should approximate small circles with patches of great circles, for example. Which, of course, it would be more expensive, but we're working on that. Yeah.
I think it's time to wrap up. So I'm told by the organisers there's no housekeeping announcements, so let's just thank all the speakers.